So we continue with the examples of conversion of potential energy to kinetic energy. We are on the point number 8, that is about simple pendulum. So the figure shows a simple pendulum suspended from a rigid support O. Its resting position is at A. When the bob of pendulum is slightly moved from A to B, its height increases. So at B, the bob has a potential energy stored in it. On releasing the bob at B, it comes back to point A during which the potential energy changes into kinetic energy. So let me explain you this thing properly so that you understand it completely well. See, in case of a pendulum, the pendulum is like this. There is a support. There is this support over here, and this is the pendulum. So this pendulum over here, we consider that this particular position of the pendulum is, let's say, A. Okay. What we do is we are going to hold this pendulum and bring it to this point. So we are bringing it to this particular point, and this particular point is taken as point B. So when you are moving, so at this particular point, when it is not in motion, right, you are going to do work on it. So work is done on it so that this is brought to this position. So because the work is done on it, that's why now at this position, the bob will have potential energy, which will be equal to, of course, mgh. Okay, so anyway, we'll not discuss about mgh right now. So it is basically this particular body which is at this particular position will have only potential energy in it. So it will be having only potential energy. Now when you release it, so at this particular position, if you release it, the ball is going to travel like this and reach this point. When it reaches this point, at this point the body has come to a point which is at ground level, hence the potential energy will now become zero. But because the body is in motion, okay, because now the body is in motion, so the potential energy got converted into kinetic energy, and hence the body will have only kinetic energy over here. Due to the kinetic energy, the body is now going to go further upwards, and at this particular point you will find that the ball is going to reach this point over here, which is point C. At this point again it will be having only potential energy. So you can see, and then when it reaches at this point, उसके बाद क्या होगा, फिर से इधर travel करेगा. At this point again it will be having potential energy zero, kinetic energy maximum. Again, because it has got kinetic energy, it will automatically go to this particular position where potential energy again becomes the only thing available, kinetic energy becomes zero, and so on. That if there is no friction or if there is no loss of any energy, then this particular simple pendulum will go on moving to and fro continuously lifetime. वो कभी stop होगा ही नहीं. Okay? But normally क्या होता है, it stops. Why does it stop? Because वो जैसे हिलता है तो air का जो resistance है, the resistance of the air, the friction is going to make it stop. So normally it stops, but if you have taken it in a vacuum, then you will find that this pendulum will never stop. Why? Because always the potential energy will get converted to kinetic energy, then kinetic again to potential, potential to kinetic, kinetic to potential, potential to kinetic, kinetic to potential, and there is never ever going to be any loss of energy. But normally there is a loss of energy due to which the pendulum stops. So we see over here that on releasing the ball at point B, okay, that we see again, that on releasing the ball at point B, it comes back to point A, during which the potential energy changes into kinetic energy. On reaching at point A, whole of the potential energy changes into kinetic energy, and due to its kinetic energy, the bob has maximum speed with which it moves to the other side up to C. So potential energy got converted to kinetic energy, and due to the high speed what it is giving, it moves to point C at the same vertical height h. So जितना ये height है, the h over here is the height between this position and this position. ये जो difference है, that is the h over here. Yeah, so at the same vertical height h, in motion from A to C, kinetic energy changes into potential energy, and the speed becomes zero at C. So it again returns to A this motion continues. So as I told you, the potential energy gets converted to kinetic energy gets converted to potential, then potential again to kinetic, then the kinetic again to potential, and so on. The movement is going to take place continuously. We see the ninth kind of an example, and this example is based on a car on a roller coaster. So we very well know that the roller coaster is the best example of kinetic energy and potential energy. See, whenever you sit on a roller coaster, what is the first thing what the roller coaster does? They always take you to a very big height. So initially जैसे हम लोग बैठते हैं उसके बाद वो धीरे से चालू होगा and they put it into a chain and then it goes on a high steep slope. तो सीधा ऊपर टक 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 करके slowly वो ऊपर जाता है. So that is slow movement जिसमें कोई fast नहीं है और वो एकदम टॉप तक लेके जाता है. वो एकदम टॉप में लेने के बाद में then it is completely kinetic to potential, potential to kinetic. Because at that point, the highest point, the car of the roller coaster has got the maximum potential energy. And then when it is allowed to go down and up and round, due to the motion, it will be, the potential energy gets converted to kinetic, and the kinetic again, because it is going up, so it goes up round. अगर 360 वाला रहेगा तो क्या 8 पॉइंट पे आया, तो इसके पास क्या है? So let's see this thing. When I see suppose the roller coaster का एक simple example लेते हैं. So the roller coaster starts from here. It is going to go like this, कट करके ऊपर लग लेके जाता है, और वो लेके जाने के बाद में at this point it goes, and then it is just going to fall like this, and then take a turn like this, and then it is going to go like this and come here. तो इसमें if you see that when it is taking here, at that time the work is done over here to give that particular car the potential energy. At this point, the body will be having the maximum potential energy, and then when it goes down, so the potential energy gets converted to kinetic energy, and this kinetic energy over here at this point will be maximum because the speed will be maximum, and due to that, the body is going to go up. So the potential energy, now the kinetic energy get converted into potential energy, so the body goes here, and then at this point again, it will have the maximum potential energy, and this potential energy allows it to go down over here. The potential again becomes kinetic, and then it moves like this and comes over here. So this way there is always going to be a change from kinetic to potential and potential to kinetic. So initially we are working on it so that you are giving it potential energy, and then the potential energy gets converted into kinetic energy, then again kinetic to potential, then again potential to kinetic, and then kinetic comes to rest. So ऐसे करके this is how the roller coaster works. So they give a simple example over here that the car on a roller coaster at position A has only potential energy and no kinetic energy. As the car comes to the position B, whole of the potential energy converts into kinetic energy. So as at B, it has got kinetic energy and no potential energy. So as I told you, when it reaches here, it has got only kinetic energy and no potential energy. Due to this kinetic energy, the car raises to position C during the kinetic energy. So when it reaches here, then it is going to move to this point over here due to the kinetic energy. So due to the kinetic energy, it is going to go into and make into potential energy. So due to this kinetic energy, the car rises to position C, during which the kinetic energy changes into potential energy, and at C, it has potential energy and kinetic energy so as the total sum of the kinetic energy and potential energy is conserved. So in this way you see that in this case they have given you the figure like this. So it's a simple figure. So at this point A, there is only potential energy, no kinetic energy. When it is going down, it has got no potential energy, only kinetic energy. At this point the kinetic energy goes here, and when it goes to point C, at that time it will be having both potential energy and kinetic energy to sum it up. So that is how the different examples are given here. So they have given you an example of some ping pong ball activity also, that take a ping pong ball, release it from a height on a hard smooth surface. You will observe that the ball after striking the floor bounces several times. Try to answer. So when it bounces several times, you know why it is bouncing, because at this point it has got potential energy. When it falls down, it has kinetic energy. When it hits the ground, the kinetic energy gets converted into potential energy, so that's why it rises upwards. So due to the kinetic energy, it rises upwards, and then again it is going to fall downwards, and this way it is going to go 3-4 times or even many times. So when the potential energy and kinetic energy of the what is the potential energy and kinetic energy when the ball is released? Yes, so when the ball is released, at that time the potential energy is maximum and kinetic energy is 0. Why does the ball bounce back after striking? Because the kinetic energy was maximum at that time when it strikes the ball, and that's why the kinetic energy gets converted to potential. And from where the ball gets the kinetic energy for motion after striking? So it is getting the kinetic energy from the potential energy which was originally present in the ball. So this was about the mechanical energy, that is potential energy and kinetic energy. Now we move on to the next part of the chapter, and that is power. One sec. So now we see the next part of the chapter, that is power. So one sec. So the next part of the thing is power. So when a body does work or spends energy, we often come across the term power spent by the body. It means we know that many times we say that you don't have that much power to do certain work. So that means you do not have that much energy to do, or we can say that when some work is done, you are utilizing certain amount of power to do that particular work. So when any energy is spent, when any energy is going to be spent, we are always going to come, or we always hear the term power over there. So for example, when you use as an now of course electricity has got the maximum kind of use of the word power, because we never say अरे power supply नहीं है, या power गया चला गया, या power fluctuate हो रहा है. तो all these things are connected to power, much more electricity. But yes, the power of electricity and the power in normally in the case of mechanics also is the same thing. It is basically nothing but the related to the work and time. So if we use an electric motor of power 1500 watt to lift water in the overhead tank, altogether, although we use the electrical energy for which we pay cost, but we say that the power spent by the pump is 1500 watts. So we say that if the power required to pump the water from the ground floor to the top floor, or the terrace का जो tank है, उसको power required is let's say 1500 watt, then we know that when we are going to use that particular pump, we are utilizing that much amount of power. So yes, this is basically, so power can be defined. So we can define power as the power of a body is defined as the rate of doing work by the body. So the rate at which the body does the work. Okay, rate means what? The time taken by that particular body to do the work. So that's why power is nothing but work upon time, or we can say the rate of doing work. Power is defined as the rate of doing work by the body. So that's why if a body performs work in time t, then the power spent by the body is power is equals to work done. So power is equals to work done upon time taken. Okay, so work done upon time taken, work done by the body upon time taken by the body to do that work is nothing but power. So power is equals to W upon T, where W is the work done in joule and time is in seconds. So accordingly, we see that power is represented by the symbol P and is also used to represent, P is also used to represent pressure, but pressure and power are different quantities. Normally we will never have any sum which will be having power and pressure both at the same time. That's why using P as pressure and P as power will not be a problem at all. So it will never happen that P kaun sa P, power wala P ke pressure wala P, not required, because whenever the sum is related to work, energy and things like that, then P will be related to power. But when it is related to the the amount of force which is going to be or the height of the water column, or the force upon area, then you know that it is nothing but the pressure. So you know when P will be pressure and when P will be power. Different person may take different time to do the same work. So we always know that. So like for example, we need to climb up the 5-story building, 5 stories of the building. Then somebody may do it in let's say 1 minute, and somebody may do it in 2 minutes. So always the power which is going to be there. So more the power, lesser the time taken by the person to do the work. So if the person climbs the 5-story in 1 minute and the other climbs the 5-story in 2 minutes, then the one who is doing the is climbing the stairs in 1 minute has got more power than the one who is going to climb it in 2 minutes. So that's why power and time are inversely related. More the time taken, lesser the power. Now, the units of power, we know that the unit of work is nothing but joule. Unit of time is second. Therefore, power is joule per second, which is given as 1 watt. 1 watt, that is WATT, named under even after the scientist James Watt. So, 1 watt is 1 joule upon 1 second. 1 watt is equal to 1 joule upon 1 second. So that's why the SI unit of work is joule and the SI unit of time is seconds. So the SI unit of power is joule upon second or joule per second. The unit joule per second has been named as watt after the name of the scientist James Prescott Watt. 1 joule per second is equals to 1 watt. The bigger unit of power is kilowatt and megawatt. So 1 kilowatt is 1000 watt and 1 megawatt is 10⁶ watt. In mechanical engineering, we often use horsepower, simple HP, as the unit of power, and it is related to watt as 746 watt is 1 HP. 1 HP is 746 watt. Now we see the factors affecting the power of a source. The first one, of course we can see easily, power is dependent on what? Work done and time taken. So it's very simple. So power spent by a source depends on 2 factors. First, the amount of work done by the source. Okay. So what is the amount of work done? Depending upon what is the amount of work done, that will be the power of the body. More the work done, more the power. Lesser the work done in a specific time, more the work done, more the power. Lesser the work done, lesser the power. Next is the time taken by the source to do the work. Next is, what is the time taken to do the work? Okay, it is dependent on the time taken. So if the time taken, now it is inversely related. So if the time taken is more, then the power will be less, and if the time taken is less, the power will be more. So if a machine does a given amount of work at a fast rate, that is in less time, more power is spent by it. So more the time taken, lesser the power required, or lesser the time taken by the machine. If the machine is doing the work very fast, that means it is a high power machine. So the power of the machine is much higher. So that is what we understand from the factors of power. So that is some examples of the power. So we see over here, first one. If a coolie A takes 1 minute to lift a load to the roof of a bus, while another coolie B takes 2 minutes to lift the same load to the roof of the same bus, the work done by both the coolie is the same. See, we know that the work done by both the coolie is the same. What is the work done? Work done is nothing but the force into distance. So, because the distance, see, force is what? What is the load it is traveling? He said that same amount of luggage. वो 100 kg का लगेज अगर है, वो 100 kg का लगेज को उन लोग को बस के ऊपर डालना है. तो दोनों में फोर्स कितना है? सेम 100 kg है. और डिस्टेंस भी कितना है? सेम है. क्यों? क्योंकि दोनों को बस के रूफ पे डालना है ना. बस इज द सेम साइज, सो द हाइट ऑफ द बस इज नथिंग बट द डिस्टेंस ट्रैवल्ड. सो बिकॉज बोथ ऑफ देम आर डूइंग द सेम वर्क, ओके, हियर व्हाट इज हैपनिंग? In one case, so work done in both the cases is the same, but the time taken, one is doing it in 1 minute and other is taking it 2 minutes. So if the one who does the work faster will have more power, whereas the one who does the work slowly is having less power. So we see over here that the work done by both the coolie is the same, but the power spent by the coolie A is twice the power spent by coolie B. The power spent by coolie A is twice that spent by coolie B, because the coolie A does the work at double time the rate. So the coolie B has taken, because the coolie A does the work at double the rate. Double the rate means he has taken half the time. Okay. Double the rate means double the rate of doing work. Okay, rate of doing work means he has taken half the time. Okay, so when I say double the rate of doing work means he can do double the work. So when I say double the work means what? वही 2 minute में Kuli A would have done this twice. So that's why he can do the work twice more. Or we can say that he takes half the time as compared to Kuli B. So this was the example for the power, and now we see the difference between work and power and energy and power. So this is the differentiation, a very important differentiation over here. So firstly, let's see the differentiation between work and power. Work done by a force is equal to the product of force and distance moved in the direction of the force. Yes, the work done is force into distance moved by the body over here in the direction of the force. Whereas power of a source is rate of doing work. So power is nothing but rate of doing work, that is W upon T. Work done does not depend on time. You can see work is not dependent on time. Work is just work. It does not depend on time. वो कितने भी time में complete करो उससे मतलब नहीं है. Work done is more than sufficient. So work done does not depend upon time, whereas power is dependent on time. Power spent depends on the time in which the work is done. The SI unit of work is joule. The SI unit of power is watt. So that is the 3 differentiations of work and power. Now we see the differentiation between energy and power. Energy of a body is the capacity to do work. That's why we say that energy and work is the same, because it's nothing but the capacity to do work. So energy is the capacity to do work, whereas power of a source is the rate at which the energy is supplied to it. So that's why the rate at which the energy is supplied to it, or the rate of doing work, that is nothing but the energy supplied to it, is nothing but power. So they are giving you a separate different kind of a definition over here, that power is also the rate at which the energy is supplied by it. So you can use this as a definition also, but always stick to some standard thing. So standard thing will always be that it is the work rate of doing work. Energy spent does not depend on time. Again, energy does not depend on time. Energy spent has nothing to do with time. So energy is not dependent on time, whereas power depends on the time in which the energy is spent. So power is dependent on time, where energy is not dependent on time. Energy, again, the SI unit is joule, and the power, the SI unit is watt. So this was the different differentiation between energy and power. So this gives us we come to the end of the chapter, explanation of the chapter. Now what we are going to do is move to the numericals, which are based on the formulas which are there in this particular chapter. So there are they are given over here 13 numericals as the solved examples. So these solved examples you can Ariel do it on your own, not an issue at all, because it's already completely solved. So what we will do is that we will start with the numericals which are there in the form of an exercise. There are 12 numericals in the exercise. So we will take those numericals, and I think I'll better make a separate video for that, so that it is properly stored. So we'll start with the numericals of this chapter in the next video.